Good night. Thanks for everyone joining our WCRP Digital Earth webinar series on the high resolution land model and land atmosphere coupling. It's our honor to have Professor Simon Dadson from University of Oxford to give us today's webinar. And let me briefly introduce Simon, who is a professor now in physical geography at the University of Oxford. And then his research in various fields in climate change, hydrology, and the Earth's surface processes. And then also publish many leading papers and then in scientific journals such as Nature Science and so on. And then Simon holds an MA from the University of Oxford, and then an MSc from the University of UBC, University of British Columbia, and then a PhD from the University of Cambridge. Besides that, he's also an honorary fellow of the UK Centre for Ecology and Hydrology, which known as UKCEH, and then where he leads the HydroGeolist project, which is a well-known famous hydrology model. And then this combined with three-dimensional model on the surface and subsurface layer to simulate water cycle for the weather and climate models. So today, let's welcome Professor Simon Dadson and to give us today's talk on the kilometer scale modeling of the terrestrial water cycle and the progress and then the prospect. Let's welcome Simon.
Great, thank you.
It's yours.
Thanks very much, Min-Hui. It's a great pleasure to be here on one of these webinars. I've watched many of them and with great interest because I think there's a huge amount of work in the community going on, which we will hopefully make reference to during the presentation. As Min-Hui mentioned, I've been working jointly across the University of Oxford and UK Centre for Ecology and Hydrology on a range of projects that look at kilometre scale modelling of the terrestrial water cycle, in particular in ways that integrate the water cycle into Earth system modelling activities, both from the point of view of understanding Earth system interactions in relation to the water cycle, but also looking at how we might improve predictions of natural hazards, floods, droughts, water resources availability, and so on. And that's really going to be the topic of my presentation today. The quotation with which I will open to motivate the need to understand the water cycle on very fine resolution is one which comes from the Global Commission on Adaptation in relation to the impact, the importance of being able to make good predictions in relation to hazardous events that are mediated by the water cycle. Giving just 24 hours notice of an impending hazardous event can reduce damage by up to 30%. And so there's a really urgent need for us to understand long-term risks relating to climate change. But there's a very palpable requirement that we engage effectively with the resolution and time domains in which predictions that we can make of the water cycle actually matter from the point of view of reducing damage to communities, to lives, loss of life, and loss of livelihoods. And it's really towards that I'm going to direct many of the modelling advances that have come from this very broad international community to see where I think the field is, where I think the field should be going, and to give just some examples of some of the work that my colleagues at the UK Centre for Ecology and Hydrology and the other partner institutes that have been part of this work have been working on. So we don't have to look very far to see the impact of climate and water-related hazards on policy. You can look at the impacts of climate change on the water cycle, but also the need for us to understand very effectively the water security imperative, which is part of the Sustainable Development Goals, the need for climate action, resilient cities even, and so on as you look across the various different Sustainable Development Goals there, all of which are in some way connected to the water cycle. That connection can be strong, and there are many of those goals which are directly linked to water. But of course, water security underpins a lot of the economic security that is experienced in many different contexts as well. Disaster risk reduction in relation to the development of the Sendai Protocol for hazard risk reduction, early warning. And of course, along the pathway to net zero, the link between the carbon cycle and the water cycle is clearly really important. The water cycle in many ways, from a geophysical and geochemical point of view, the water cycle in many ways drives the carbon cycle. And in many other ways, it's the water cycle where many of the early stage impacts of climate change are felt most acutely. You can see that in a number of statistics that are drawn from some of the IPCC reports that have come out lately. Heavy rainfall events likely to become or 50% more likely than the baseline average. Drought events twice as likely as the baseline average. And a rather striking statistic that by 2050, over half the world's population projected to live in water-stressed regions, and almost 2 billion people projected to live at risk of floods. Those are projections, but we can look at the data. In fact, this is a paper which some colleagues of mine published just yesterday, showing that accelerated impact of global drought has already hit us. It's already come through in the historical record. Global drought severity increased since 1901, with we calculated 74% expansion in global area under drought. And the water cycle changes which mediate this drought are not just through changes in precipitation, they're through changes in air temperature, humidity, and the factors that control the interaction between the land surface and the atmosphere. And so a large fraction of that change in global drought severity is driven by the energy balance, the evaporation at the land surface as well. And rather alarmingly, in 2022, almost one third of the global land area was impacted by drought, according to the analysis which is presented here. It's all very well to look at global picture, but of course this webinar is looking at kilometre scale modelling of the water cycle. And it becomes even more important that we address our attentions to producing finer grained projections of what might happen in the future, and that we develop models that are able to tell us, where it's possible to do so, what the spatial and local impacts of the changes that we're looking to see or thinking that we will see in the water cycle are going to be. And I won't go through them all, but I've just got a series here of impactful events, hammering home, I hope, the point that there are 2 billion people in the world that lack access to clean, safe drinking water. And in many cases, that water scarcity is compounded by the lack of available clean drinking water to sustain lives and to sustain livelihoods. There's also a clear impact on the economic system. Some iconic droughts that are described here causing several billion euros or dollars or pounds worth of economic damage, and requiring policy responses that, while they may have begun in many local contexts, have impacts that extend to the broader regional context and which extend globally as well. The catastrophic scale of famine in East Africa in 2011-12 and latterly in the last half of the 2020s as well has caused a great deal of tragedy and many terrible events that have arisen from the food and water security implications that arise from events such as that. At the other end of the spectrum, of course, flooding is estimated to cause $120 billion of losses from urban flooding, which requires a level of spatial resolution to localize the responses. And there are just 4 examples there, each with a very high price tag, both in terms of human lives lost in some cases and economic damage. The regional impact, for example, of the Libya floods, which obviously affected people across communities, children, impacted healthcare, education, clean water, and so on, were clearly catastrophic. But even closer to home, we don't, closer to my home, we don't have to look too far to see highly damaging scenes, which are shocking for the year, in this case, year 2021 in Western Europe on the Rhine, causing a great deal of monetary damage and tragically loss of life there as well. So I hope, by way of motivation, the need for finer and finer resolution projections of changes in the water cycle is clear from some of these examples. The community has alighted on kilometre scale projections. I don't deny that kilometre scale projections can be, in some cases, too coarse still. From the point of view of atmospheric modelling, kilometre scale is an admirable ambition, and much of our work is directed towards that sort of canonical scale, which matters enormously because you begin to resolve important processes in the planetary boundary layer. But of course, a lot of the impacts that I've described both require us to go down to finer resolution than that, and also draw on parameterizations and processes that are happening at finer resolutions than kilometre scale. And so it becomes a really interesting technical challenge and an interesting conceptual challenge to try to bring together some of those processes that need to be incorporated into interacting Earth system models, and also to describe the outputs from projections that those models make in ways that can be useful to decision makers who either have to respond to conditions when they arise, or who have to generate policies based on uncertain information. So the programme that I lead at the UK Centre for Ecology and Hydrology is called Hydrojoules, and it's really about equipping us with the next generation capability to make kilometre scale predictions of the water cycle, using a range of different models, all connected through the Joules Joint UK Land Environment Simulator, but designed in such a way that they're to be interoperable and can be shared, open source, and drawn upon by people in different communities across our broad area of science, in order that we can begin and sustain the sorts of dialogues that are necessary to draw in a range of interdisciplinary scientists to address some of the really pressing research questions that are highlighted on the screen. I focus on these questions because they're questions that have emerged from the many consultation exercises that we've undertaken as part of this programme. Broad scale questions like how will climate extremes and land cover affect flooding? And these are questions which you can't answer using simple models that don't include feedbacks between those processes. You have to have models that represent ecosystems in functionally meaningful ways. Questions like, will future heat waves worsen drought? And it's obvious that not representing many land atmosphere feedbacks in models of the water cycle is going to hamper our ability to make good predictions of heat waves into the future. How can we use new observations from Earth observation platforms, but also from field sensors that are being developed in recent times? How can we use those new observations to reduce the uncertainty in our projections? And a really interesting question around how humans are changing the water cycle. We know that in many river basins, Colorado stands out, but in pretty much every river basin in the UK, the impact of human activity on the water cycle is order of magnitude equivalent to the natural fluxes. And so if we don't include the role of humans and decisions that humans make in terms of reallocation of water, transfer of water between river catchments and regions, impoundments and irrigation, for example, if we don't include those anthropogenic processes in our analysis of terrestrial water cycle, then we miss a really important first order flux in the system. What sorts of new observations and modeling technologies do I think we need, and what's been our guiding focus? Well, there are some examples there of the very fine resolution kilometer scale atmospheric, global atmospheric land and ocean coupled model that is at the heart of this type of Earth system modeling. And a timeline from a very clear paper by Rosie Fisher and Charlie Coven, looking at the way in which different aspects of the Earth system have been included into land models over the historical past. We especially want to focus on the types of model which represent the terrestrial water cycle interacting, components of the terrestrial water cycle interacting with one another in a functionally relevant way. So interacting with the fluxes of energy, water, momentum, and so on in the various interface points that they have, and also to understand where, for example, those interactions matter the most, where tipping points become relevant, where the feedbacks between different components of the Earth system are important to focus on in order to understand the dynamics of the system. We want to understand where it's possible to reduce uncertainties, and often by doing benchmarking experiments and model intercomparisons, it's possible to see the uncertainties in our models and see the uncertainties in different components that make up those models to target future research towards the areas that are most likely to improve our predictions the most. To move smartly to high resolution community-based land system models. And I say smartly because there are some areas where the trade-off between computational requirement and high resolution sometimes doesn't add very much to decision-making power, and sometimes it adds an enormous amount. There are occasions, of course, when one is better off with a large ensemble of relatively coarse resolution models in order to capture uncertainties and to understand dynamics and patterns in modeling approaches. And there are other situations where that high resolution is very important. But in all cases, understanding the uncertainty that arises at every step of the chain is crucial. And I couldn't give a talk about this without referring to artificial intelligence, machine learning, data assimilation, and digital infrastructure, which are lots and lots of ideas all grouped into one bullet point. I'm not going to talk in any great detail about any of those, but it's very clear that artificial intelligence approaches are moving very rapidly, and we need to harness those. People around the world approach the different technologies with different levels of enthusiasm, and the critical reception of many of those ideas has previously been patchy. But I think it's fair to say that in the last 5 years, they have really proved their utility in simple cases, making good predictions where otherwise we might not understand the system sufficiently to do so. In other cases, helping us with discovery of new parameterizations, guiding our additional observations as we move to improve field observations and move to add new data sources to protocols and so on. And also in their more traditional forms, looking at data assimilation, we've seen massive advances in ocean and atmosphere data assimilation, and data assimilation using traditional protocols and protocols that have been informed by techniques from machine learning are destined to make big advances in the way we understand the land system as well. So I'm just going to give a flavour of some of the things that we've been doing in hydrojoules. One of these is looking at very fine resolution representation of groundwater systems. In many studies, groundwater availability is identified as both crucial for water resources planning, but also a missing process in coupled Earth system models. And this piece of work, which has been led by my colleagues at the British Geological Survey, takes a very large archive of historic borehole logs and groundwater data and brings it together in a digital form, which goes down in depth into the Earth's crust, down 400 meters, and characterizes the conductivity, specific yield, and so on of the aquifer systems that underlie the land system elements that we're dealing with in the UK, and has proven, as you can see on the right hand side, and has proven to increase our ability both to represent soil moisture at the surface, because we get the lower boundary better constrained in coupled land atmosphere simulations, and also to give us regional picture, quick look for situational awareness, regional picture of groundwater availability in times of water scarcity and water stress, which is acute particularly in southeast UK in many times of the year. So drawing on those otherwise unused data sets to represent processes that we know need improvement in land system models has been an important step in moving towards that kilometre scale approach. I mentioned data assimilation a little while ago, and this is an example of using data assimilation for parameter estimation to improve the UK scale picture of soil moisture through the development of a prototype system that draws on both the Joules model, has the Joules model as at its heart, but draws on a range of, in many ways, uncertain satellite data products and the field scale soil moisture sensing equipment using cosmic ray attenuation under the COSMOS program to improve our representation of soil hydraulic properties in the Joules model over the UK, so that we can make better predictions of soil moisture, regional predictions of soil moisture that are able to be updated in near real time for applications which are important in terms of water resources management, agriculture, agricultural water availability, and looking at groundwater flooding from the point of view of situational awareness. So that data assimilation approach, of course, is able to account for data sources of with differing uncertainties, and gives us a good deal of scope to improve predictions, but also to understand what additional physics is necessary by looking at the reasons why models aren't necessarily performing well when used in that way. A third example is looking at coupled modelling of the water cycle, and here it's really getting to the heart of that connection between the water cycle driving the carbon cycle. So some excellent work by my colleagues Toby Matthews, Rob Parker, and Hugh Lewis here, looking at in the top panel the seasonal inundation of Amazonian wetlands and the impact that has on the generation of methane plumes. Rob's study takes the same physical approach, but looking here at the emission of methane from the Sud seasonal wetland in the Nile Basin, and here you can see around the Sud the simulation, the accurate simulation of methane emission from the seasonal pulsing of water flowing through the Sud wetland, a process which is very hard to represent unless you have that close coupling between the water cycle, plant physiology, and land carbon processes. And so this is all done with the Joules model, and that interacting aspect of the carbon and water included within Joules is very helpful to have represented in this case. We can go further still and connect the Joules land system model with CAMAFlood, the surface water inundation approach from Dai Yamazaki's group in the University of Tokyo, and in the case of the bottom panel, the NEMO coastal ocean and shelf seas model, to see here a fully coupled atmosphere, land, ocean model where we can track freshwater plumes moving into the ocean. This is especially useful for the shelf seas around the UK, looking at water temperature, impacts on biology and so on. But as a capability, it will prove itself when applied at the global scale, looking at freshwater delivery to ocean basins and the role in which that will play when looking at climate tipping points in Arctic and tropical settings. So this is really the direction of travel from those global models through applications relating to local meteorology to the points at which the risks are truly experienced by communities. at the very finest scales. And the hope is that through programs like this, we're able to contribute components to the community and also work collaboratively with domain experts in particular fields to draw on components of very well-established models that can be included in systems like this to address these problems which are not confined to a particular scientific discipline, but which bridge across many different disciplines. In order to do that, it's very important to be able to engage the community on a scientific level, but also on a technical level. And so one of the resounding requirements that came through when we were developing this program is how do users get access to the program with different levels of computational sophistication. And so we've split our user access modalities into three. There's a first tier which uses a technology called Data Labs, essentially a Jupyter notebook hosted on a server, which also has a number of very large data sets available for students, for early stage graduate students, even undergraduate students using this Data Lab system, so that they can come in and with very little overhead get to grips with a Jupyter notebook. And I'm just running through some screenshots here. Jupyter notebook, and in a matter of perhaps an hour, can get to the stage where they're extracting data from the pre-computed data sets that are available through this system, producing maps of various kinds, extracting data, collapsing data, doing their own analysis, maybe running simple models as a result of that. And we found this to be a particularly effective way of engaging early stage undergraduates, even through our summer schools that we run, which use this component as a way in for people to get fairly straightforward access to data sets and to begin collaborating. We also have a deeper way of engaging for those who want to run land system models themselves, particularly Joules via the Jasmine data intensive supercomputer, the ethos of that being to take the computational task to the data center where many of the data sets are held. So we have several petabytes of data held in the CEDAR archive, which are accessible through the Jasmine data intensive supercomputer, which allows people to collaborate via a group workspace hosted on that machine, so that they can do so from anywhere in the world with their colleagues, without the overhead of having to download large data sets and move them across to different servers. And then, of course, the final tier, which is around developing code and contributing code to the code repository itself, and that we do using a series of interfaces which are depicted in the picture here, really to control the way in which information flows between different modules, and to do so in a way that is clear and defines those interfaces in a predictable and sensible way that's true to the physics. And of course, at the heart of that is around the need to build the community at the same time as building the model. And it may be helpful to advertise this series of opportunities amongst the group assembled on the call here. Before I draw the presentation to a close, we have a summer student program that has just appointed its summer students for this upcoming cycle, but anticipates appointing some more students to paid internships, typically to current graduate students who want to come and work on problems connected to this field for a period of time over the summer. We also have, and possibly more relevant to those on the call now, we also have a visiting scientist program which invites collaborative proposals to be developed with established scientists who would like to collaborate with one of our group, and will fund a research visit either from somebody in our group going to a partner institution, or somebody from a collaborative institution coming to work in one of our institutions, and it's been a great way to seed new proposals and to get people talking about new opportunities that might be relevant to this sort of science but not funded directly within it. And finally, let me say that we have our annual conference, which sometimes runs online, but is running in person this time round. The registrations will open very shortly. The abstract submission deadline closed quite recently, but registrations for the meeting itself will open very shortly. That's a meeting to be held in London at the Royal Society in central London in mid-September later this year. So if anybody is interested in that, please feel free to get in touch with me, and I'd be only too pleased to point you in the right direction. Min-Hui, I think my time is up, so I'll hand back to you.
Okay, great. Thanks, Simon, for these introductions and then illustrate about hydrogeolus, how we can utilize this for various purpose. And especially in the beginning, you mentioned about like kind of climate services concept, like how this can use to prevent this hazard. Well, thank you very much. And then everyone, so if you have any questions want to ask Simon, you can put on the over the Q&A box that type your questions, and then Simon will go through it.
Yeah, very glad to take questions. I can't see any questions at the moment, Min-Hui. I don't know if that's because I'm clicking in the wrong place, or perhaps nobody has any.
Yeah, no, not yet. So
fair enough.
Yeah, maybe I can. Oh no, sorry, there's one here.
Oh, here comes a question. Yeah.
Yes. Can you see it?
Yes, I can. Yeah, I'll read it out just to check that I've understood the question. So as models get more complex, the amount of processes represented, and we increase resolution, the amount of morphological data sets increases exponentially. In areas of the world where these data are not available or at very coarse resolution, what are the best modeling approaches? Because complexity and resolution can produce more harm than good. Yeah, a really, really good question, particularly where you have a highly sensitive system, which and soil moisture in areas where atmospheric convection is very sensitive to soil moisture is one which stands out for me as being a particularly obvious example of the point that the questioner is getting to. I think here I referred to in my presentation to some circumstances where we really like making fine resolution projections, and we need fine resolution projections in areas where, for example, for the area that I'm looking out at from my window in Oxford, we have centimetre scale data sets that characterise the orography, that characterise land cover, and so on. There, the real challenge is folding the data that we have into a suite of processes or a suite of modelling applications where the processes can be represented in a computationally effective way. Whereas the questioner is sort of getting at the opposite challenge, which is where we have, perhaps one rain gauge in a 500 kilometer radius. And I think this is where it's tempting to say that technology such as Earth observation or big data, machine learning, those types of things will come in, but those work very well in contexts where we have more data than we have ideas. In many of the settings that are referred to, we have very, very few data to constrain the processes that we're trying to understand. And so surely the only way to make long-term progress is to divert some of our resource into collecting more data in those areas. There may be technologies that are more efficient at doing that than the standard hydrological technologies, but I think the long-term progress will come only when we start to value those types of observations in ways that we might actually have done in the past, but have stopped doing now. So we need more observations is my first answer. The second answer is in the context of having no observations, we simply need to be honest with the uncertainties, and that requires a series of experiments that probe those uncertainties and understand where the uncertainties arise and what might be done to constrain them better. So it's not much of an answer, I'm afraid, but that's about as much as I can give at this stage.
Well, thanks, Evan. But just want to follow up this question. So how about the satellite data can be used for those situations, not many in-situ observations?
Yeah, I think there's a really interesting question there, and obviously new Earth observation platforms coming online and sensors coming online, in very rapid succession. A few of my graduate students and postdocs have been working with the Planet Labs offering, which is incredibly rich in detail. And I think in some ways we underestimate the information that can come from some of those very high frequency, very high resolution satellite products. And possibly the value here is in developing novel algorithms that can see what is missing in the way that we interpret those sources of information. Having been quite skeptical of some of the neural network approaches that have been used in machine learning. I have to say that about, what is it, 4 years ago, stymied by the COVID pandemic and the inability to travel, one of my graduate students sought to see whether he could simulate river flow using a very small number of observations from gauges across the UK. It was. And it turned out to be much more successful than any of our physically based models, possibly to the surprise of some people, and actually to the very pleasant reaction of others. Essentially telling us that there is information in the data that we have that we haven't yet extracted through physically based process models. So I think there's a lot of hope, and the hope is that people will be able to take many of those satellite data streams and perhaps link carbon, water, energy, and food by taking new approaches to the ways that information from those data streams are used in our large scale models. So I think there's definitely an amount of science discovery that can come from applying those approaches in ways that don't simply seek to make better predictions. They seek to understand why the predictions are being improved by the use of that new technology.
Yeah, that's a good point, to understand what happens.
Yeah, exactly. Yeah. There's another question there from Francesca. Thanks for your time. My question is,
Yes.
do you consider a technical challenge having high resolution forcing for a land model which aims to have high resolution outputs? ERA 5 as a reference. What kind of forcing for a regional model, Jules? Yeah, we're sort of agnostic to the forcing that's used. In the UK, we're using forcing which, for the historical record, comes from a very high resolution rain gauge data set that's interpolated using a regional interpolation algorithm, and so is considered to be as trustworthy as we can get in that sense. And for the future simulations, we're using kilometer scale, usually 1.5 kilometer scale atmospheric projections to connect into joules in most of the examples that I've given here. The uncertainties in you mentioned ERA 5, for example, and some of the other global products. The uncertainties in those are, of course, a lot greater than uncertainties in interpolated historical data. And so it's necessary I think, to be flexible in terms of the data that go in. And then there's a few questions coming in now. Jan Peter Schultz, thanks for your presentation. Urban flooding intensifying with global warming, yeah, and using MORUSES, which is an urban surface exchange scheme in the Met Office model. Yeah, I have to say the approach we've taken to urban flooding has been to do those simulations minimizing the land atmosphere feedback, and so to regard it almost as an impacts problem, simply because there you cross over into a domain where 1 kilometer, I said at the beginning of my presentation, 1 kilometer is considered to be at the finer end of the spectrum for atmospheric modeling. By no means the final word, but at the finer end of the spectrum. Whereas for urban flood modeling, you can phone up an engineering consultancy and have a centimeter scale model of your flood reach or your river reach produced within a few weeks. And so the standard is to use much finer resolution data for which the feedbacks are not practical and probably not on the timescales of note, probably not to be simulated. And so that's the approach we've taken, simply because the impact is the dominant driver of the requirement for that type of output. Where it is that we need flood inundation modeling for Earth system applications, we've tended to use the more generic types of model like hammer flood and other sorts of approaches, where the model is capturing subgrid variability, but doing so in a way that's computationally parsimonious and therefore able to coexist with with an interacting suite of Earth system modeling processes. Whereas in the case of an impact study in an urban area, the dominant requirement is the resolution for the topographic data in my view. And then I think this is Luis's the questioner from before. There's not enough data to adapt the satellite retrieval algorithms and inconsistency. Yeah, of course, I wouldn't claim. I don't think I would claim to want to rely on those metrics and so on solely in the absence of anything else. It may give us some interesting data to include, but clearly innovating to such a point as we can measure processes on the ground is clearly the only way to drive forward progress in those areas. It's sad that focus has often been on improving some very expensive sorts of technology at the demise of in situ rain gauges and so on.
I see. Yeah. Cool. Yeah, if you have any further questions. And Yifan, do you want to say something?
Yeah, so I just noticed I cannot put the question in the Q&A, so I might as well just ask this online. So I also noticed you put AI over there, and I'm curious whether you can elaborate on whether you have noticed any opportunities that we can leverage AI to help us move towards a high resolution process-based modeling. Yeah, so that's overall my question. Yeah.
Yeah, really interesting question. I think in a way there are three sort of entry points into answering that question. One is the very immediate requirement for model outputs that match observed. In my case, it's often river flow that we're trying to get right. And for times, it's essentially a time series problem. Sometimes there's a spatial element to it, but it's essentially a time series problem. And for time series problems, the long short-term memory convolutional neural networks are incredibly effective. If you have input rainfall data, and you have some river discharge data to train a model against, we've found that they can produce highly satisfactory results, which would be considered credible by the standards of a bespoke flood early warning system. So there are some excellent potential applications there. The second slightly more elaborate answer is to say, well, that's all very well, but you run the risk of overtraining models. You run the risk of all the sort of perils that come from any data-driven approach. And I think the sort of data fusion angle, what we might have called data assimilation, and not been too worried about giving it a name that had anything to do with AI or machine learning. Those types of algorithms are really only beginning to emerge in terms of their promise when it comes to land terrestrial water cycle. They've obviously made a huge impact in atmospheric modeling and so on. But that data assimilation project, I think, is absolutely crucial in terms of retaining the physics that we know can persist and be valid over times outside the training window that we have for empirical models, but adding a layer of improved predictability using that sort of approach. And I've seen a number of framings of that data assimilation problem that are enhanced by the machine learning, by the neural network approach that has worked so well for time series modeling ab initio. And then the third is a more recent innovation into what might in the field of artificial intelligence or machine learning be referred to as interpretable AI or explainable machine learning, where you're doing it not simply to increase some goodness of fit score, you're doing it to understand what concepts are being learned by in many cases a neural network model, but there are other structures as well that are just as effective, if not more. And I think that is a really important stepping stone towards using those technologies to try to understand what signatures, what process representations might exist within large data sets that we have, but which we haven't fully made use of. And by definition, I can't really tell you what those might be, but I think there's a sense in which in many fields of science, those who are keen to embrace those opportunities have had great success. So I think in the field of water cycle simulations, there's a lot to be drawn upon there.
Yeah, agree. Well, thank you very much, and thanks Yifan for raising this question. I think the machine learning or deep learning approach is definitely ongoing work. Try to improve the model simulations. Yeah, and then I know some of the parameterizations can be like replaced by this machine learning tuned process, and then the speed is much faster. So should be more and more process will be invaded by using that kind of approach.
Yeah, absolutely. I think the computational speed up and so on will will be evident in lots of different ways, as we've seen. Colleagues in atmospheric modeling have seen that already, and I think that will come to us in land modeling as well. In fact, we are in many different contexts re-engineering the algorithms that we use for the standard calculations in a lot of these models to take advantage of the differently structured computational resource. And so actually in the short term, the main impact of artificial intelligence may simply be the sort of brute force computing availability that comes from that, and the improvement in computational resource use that comes from re-engineering those things. As someone said to me a couple of weeks ago, when the spreadsheet was invented, it caused a dip in global corporate productivity because people had to spend time learning how to use it. But then of course it's caused a rebound, which is notable, and now we teach spreadsheets to 7-year-olds in school. The same will probably be true of the type of computation that's now routine in machine learning, artificial intelligence circles, and so it's not easy for someone who hasn't grown up in a world with those things available, but pretty much everyone that's coming through the system now, being trained now, is very acutely aware of those different technologies, and is learning quickly how to make use of them.
Yeah, sure. Well, cool. I think the time is also up. Well, thanks again, Simon, for sharing, and then discuss with the audience about the hydrojuice model developed. And then also share with the information about summer school and then upcoming workshop in September. So everyone can register if they are interested in this hydrological cycles and using. So it's particularly using the hydrojuice model or not
No, it's a
necessarily?
community workshop, so it looks at the themes that are within the scope of hydrojoules, but is not particularly focused on hydrojoules at all.
Gotcha.
It's open to anyone using any model
Everyone.
or anybody who'd like to talk about those sorts of big issues.
That's cool. Great. And then again, thanks, Simon. And we will have another one in 2 months, which is in August. And then if anyone wants to share your research in this high resolution net model and then atmosphere coupling, please let me know. We will try to arrange it. All right, great. Good to see
Fantastic. Thank you
you.
very much, Min-Hui. From me, thank you very much for the invitation to present. And it's been a pleasure to meet you all and to have such good questions.
Very good. No, thank you.
Thank you, Simon.
Hope to see you soon.
You're welcome. Thank you. Bye-bye.